Well, hello friends. Welcome back to the program. Today we are going to work on multi-core stability in Serenity OS. So we're going to run the system with multiple CPUs and then very likely run into stability issues, deadlocks, all kinds of trouble. And then we're going to try to fix things as we encounter them. And this is the whole reason that the system by default runs in single processor mode, because multi-processor mode is very unstable, as we'll soon see. So the first thing I need to show you is how to boot the system in that mode, actually. So I typically use the serenity.sh script, and then you would say something like this. So run architecture toolchain, and then you can pass compile or kernel arguments. So here you would say SMP on. And I'm also going to pass disable KASLR to turn off outer space layout randomization for the kernel, which will allow us to attach a debugger. So you just run that command and it will build and create a disk image and then boot into it. And we should be in, so as you can see here, we have two CPUs, although nothing is actually being scheduled on the second CPU. That is because even though we boot with multiple CPUs, we still don't actually schedule threads on the secondary or any secondary processors by default. So if you open scheduler.cpp, in the kernel, you'll find this thing here, schedule on all processors. So we're just going to turn that on by setting it to 1, and then we'll do a quick rebuild, hopefully quick. And then we should be able to boot into a system that actually schedules on both of these CPUs. And we'll see if we can actually get to the desktop. Sometimes, in the past at least, it would hang before you would get to the desktop. Okay, so we are up and running. Cool. Let's set that. Yep. And as we can see, we are actually getting CPU activity on both processors. So an easy way to stress it a bit is to run our JavaScript test suite. And maybe you can even run it twice in parallel, like this. And we can see that it is indeed using up both CPUs. And there is our first kernel panic. It didn't take too long. So let's see what's going on here. So we have an assertion failed. Processor current should be this, but it is not. In check invoke scheduler. So because we had the foresight to disable KASLR, we are now able to attach GDB to the kernel. I have my GDB configured to automatically connect to our kernel. I think I have that in my GDB init script. Yes, this stuff right here. So it just automatically connects to our QEMU GDB server thing and asks for a backtrace. So as we can see, there are two threads. That's how the CPUs are represented here in GDB. So thread 1 is basically just idling, and thread 2 is the panicking CPU. So here we have the assertion failed, and we are in processor check invoke scheduler, where something has gone horribly wrong. So let's go and actually look at that. So processor CPP 996. Okay. Check invoke scheduler is checking that processor current is this, and apparently it's not this. So okay, so who called this? It was non-null ref putter exchange. That sounds like something got inlined. Okay, so it's in processor.h. and in processor CPP. So it's probably being inlined from places. Always inline. Do leave critical. All right. Who else? Clear critical. Okay. So probably one of these two. So I think we are exiting a critical section in the kernel, and when we're doing that, I think typically we enter a critical section with interrupts disabled, and this happens when you grab a spin lock, for example. Then we set this flag on the CPU that now the CPU is in a critical section, and then that means that nothing else will get scheduled on the CPU. So you're kind of guaranteed to keep executing that train of thought or train of code on that CPU until the critical section is over. So it's like a synchronization mechanism. And check invoke scheduler would be called when we're leaving a critical section. So min critical is a counter, and right, so we can have nested critical sections. So entering a critical section, enter critical, increments the critical section counter by 1, sure. And then when we leave a critical section, if we are leaving with min critical 1, that means that we're actually leaving the outermost critical section and transitioning to non-critical section execution once again. And at that point, we will execute any pending deferred calls unless we're in an IRQ. And we will also invoke the scheduler. Wait, how does that work? So we check if we should invoke the scheduler. Okay. So, all right. So I think if I remember how this all works, it's that while you're in a critical section, if something happens that makes us decide to run the scheduler, to like switch to a different thread, for example, then we don't actually invoke the scheduler right away, but instead we set this flag called invoke scheduler async. And when we then exit the critical section, then we invoke the scheduler at that point. So if you were to call like schedule a new thread, then while you're in a critical section, we don't actually schedule a new thread until the critical section exits. And that is, I think that's important in stuff like when unlocking a spin lock or a mutex or something like that. Okay. So let's see. So we had the error was that we're not on the processor we think we are. Processor current should be this. Okay. So check invoke scheduler. I think the first thing I'm going to do is I'm going to move that stuff out of line, because I am skeptical that that stuff even wants to be always in line. The leave critical stuff, and it just makes it harder to understand the backtrace anyway. So let's start by doing that. Okay, we'll take that code and we'll put that right here. Okay. And leave critical, whose only job is to call do leave critical. It's kind of weird. I think that could be out of line as well. Okay. So if we do that, we should at least get a nicer backtrace. Now, of course, it's kind of tricky because we can try to provoke the same bug again, but we might hit something else instead. So instead of just rebooting, since we don't have a super reliable repro here, I was just kind of prodding the system until something happened. We are just going to stay with this backtrace that we have right now, and continue looking at the code. But I think I'm gonna make sure that this builds, and then I think it's okay to put this out of line. I don't know why this would need to be always in line. That seems overly, I don't know, seems overly excessive. So let's do a commit. Kernel move processor leave critical out of line. I guess this is kernel x86, actually, specific to x86. Don't think this code needs to be always inline, and moving it out of line will make backtraces nicer. Okay. So why would we be on the wrong CPU? So what makes us think that we should be, let's see. So we're calling this on a specific processor, right? Here, this is this the only thing that calls that? Yes. Okay, so leave critical is a static function in processor. So it does not have a this, but then it calls current, which gets a pointer to the current, currently executing processor. So I guess one thing that could happen is that, what if you get interrupted or preempted after you call after current, but before do leave critical? So say that you are on, we have two CPUs, and then you are on the first CPU, you call current, you get a pointer to the current CPU, and then you get preempted, and then you get rescheduled, but now you're executing on CPU 1 instead of CPU 0. Then you would be calling do leave critical with the previous CPU pointer, I think. Yeah, right? So the easiest solution to this that I see would be to just disable interrupts while we do this. And that just means that we don't actually allow us to be preempted here. So whatever the current CPU is, there will be no chance for a preemption in between here. Because check invoke scheduler started by disabling interrupts anyway. So that is kind of weird. So whenever we're doing a check invoke scheduler, we are actually assuming that you're being called on the current CPU, and that we are not in an IRQ, and that we are not in a critical section. Oh, interesting. So these assumptions are actually very interesting here. So I think maybe what we want to do, instead of disabling interrupts here, we want to verify interrupts disabled, and then we will require our caller to have disabled interrupts instead. So we had a couple of places that were doing this. Clear critical was also doing it. This guy's doing it here. He's already verified interrupts disabled. Do leave critical. I mean, I guess this stuff here could just be folded into one function. Although it's a little obnoxious because it's convenient to call it on an instance here. Yeah. This seems fine, but then we just need to make sure. What's the nicest way? I guess we could use the type system for this. So we could say when you call check invoke scheduler. Well, I was going to say when you call check invoke scheduler, we could require that you pass in an interrupt disabler just to prove that you have one. But maybe interrupts are disabled through some other mechanism at one of these call sites. I think this one, like verify interrupts disabled. But we don't have a disabler here. We're just being called with interrupts disabled. Yeah, so we can't do that. Okay, so that's fine. Let's see. So check invoke scheduler. Was there someplace then that I needed to actually disable them? Oh yeah, this place right here. Clear critical. So what does clear critical do? Okay, so we use it in yield. And as you can see right here, interrupts should be disabled. Clear critical. Relock process. Okay, so I think we probably want to disable interrupts in here as well. Also, we can probably move this out of line. It's weird that all these things are in line. It does not seem necessary. Like something like this, I can understand that we would do inline if we're just doing a simple read from the GS segment. The GS segment in the kernel, by the way, points directly at the current processor data structure for the current CPU. So that's how these accesses work. Doing that in line kind of makes sense, but more complex logic like this stuff, So let's see, let's move this out of line as well. Yes, okay. Clear critical. Can we, let's see if we can do that as a as an amendment to the previous commit. Yes, we can. Leave critical. Yeah, so leave and clear critical outline. Okay, and then when we clear critical, we want to make sure that interrupts are disabled. Yeah, because otherwise you have the same race here. You're grabbing current, stashing it in a variable called proc for some reason. That's a really awkward name. Yeah, so let's interrupt disabler. And then I think we can do something like that. Yeah, at the same time, yeah, I don't want to touch too much stuff, even though the variable name is crappy. It's outside the scope of the change. Okay, so let's see. So what are we doing now? We are disabling interrupts when calling clear critical. So clear critical and leave critical will now both disable interrupts. And I think maybe the next commit we'll do will be just to clean this up and then maybe fold this stuff into a single function, just like clear critical. Okay. So kernel. Oh, wait, hold on. We should test this. It's a little too optimistic there. Started thinking about the commit message before even building it. That is not the best habit. So, let's see if my ice cream cluster is working. Wait, it's not sending any jobs to the other machine. Okay, let's do some more jobs here. Ah, there we go. Compiling across 2 computers. Very, very cool. Yeah, I guess I have to tell Ninja to use enough jobs so that there's translation units to go around for both compilation servers. But yeah, this is really nifty. Okay. Should be done here in a second. All right, so let's try to boot. Oops. We are up and running. We have 2 CPUs. Oh shoot, no, we are still scheduling on all processors. Did I accidentally commit that in the previous? Come on, that was sloppy. We gotta fix that. But yeah, we're scheduling on both CPUs. Okay, good. Test.js. So let's see if we can run those things in a loop. See if we can provoke the same crash just by normally like just moving windows around and irritating the system a little bit tends to provoke some kind of crash. I know I've definitely seen the same backtrace that we got today. I've seen that before many times, but never actually looked closely at it. So I'm glad that we're doing that. It seems to, at least so far, we're not dead. So that is great progress. Let's see if we switch things around here a little bit, click on other stuff maybe. That's pretty cool. Maybe start some fire. I have to say that stability appears to have already improved considerably. I don't remember running SMP for this long before. So that is cool. Now I guess we can try to throw some real wrench in the gears by running our full test suite. There we go. That's more like it. Yeah, so just running the whole Serenity unit test suite killed us. Cool. In the Chadir syscall. All right. And that is recursive spin lock unlock, where we are seeing an assertion failure. So mlock load, so that's an atomic load of mlock, should be equal to processor current. Sounds like we might have the same type of bug elsewhere. So I think I'm going to go ahead and say that this is a very reasonable change, the one that we have. So just disabling interrupts like this in order to make impossible preemption after grabbing the current processor pointer and calling a function on it. Kernel x86. Disable interrupts when leaving, clearing critical section. Yeah, on leaving critical sections. Because that's what both of those things do essentially, right? So clear critical also it wipes the mn critical to 0 and then saves the critical section counter. So actually, what do we even use that for? For yield without releasing big lock? Yeah, that's a really weird behavior. Like, why would we want to clear critical? I think this is probably some awkwardness. I think we should be able to get rid of this once we get rid of the big lock, because we shouldn't do context switching in a critical section. So I think this is primarily something that we are forced to do right now because of our big lock semantics. Our big lock, process big lock mutex works in this way that it is unlocked when a thread wants to block in the kernel. Then we automatically unlock the process big lock. And there's like this special weird behavior around that we allow you to yield with the mutex held. Anyway, yeah, I think this API will eventually go away. So it's essentially just a way to immediately exit a critical section and return the nesting level of critical sections so that you can then re-enter at the same nesting level once you resume execution in that context. Okay, so this fixes an issue where we could get preempted after acquiring the current processor pointer, but before calling methods on it. Strongly suspect this was the cause of processor current this assertion failures. Yeah, that it seems very, very reasonable to believe that will be the cause, since it's clear that you could get preempted after getting the pointer. Okay, so yeah, do we want to fold this in the same way as clear critical is folded? So like this, basically. And then it would look something like this. It's a little bit awkward to type current so many times. Do I dislike it? Kinda. Well, this is not very aesthetic. I guess it was okay the way it was with the helper. Okay, fine. Let's leave it alone. And instead, we can investigate that other issue. I just want to make sure that I don't accidentally enable scheduling on all processors for everybody. So let's just fix that up. There we go. And then now we had that other problem to look at. Did I catch that with GDB? This is the first GDB. Oh shoot, I've already killed the VM. But we had at least this to go on. So we are in Chadir. The Chadir syscall, and we're doing a recursive spin lock unlock. And then we are expecting mlock to be the current CPU pointer. So let's look at spinlock CPP. Line 58. Okay. So what are we looking at here? This verify is failing. So we're expecting mlock, which is an atomic flat putter. Sure. So we're expecting it to contain the address of the currently executing CPU's processor pointer. And why wouldn't it? So, recursive spin lock unlock. Who would have called it? Syschadir. Recursive spin lock. I guess this is spin lock protected, maybe. Yep. Okay, so spin lock protected. Spin lock protected with does a lock and and then it will unlock when it goes out of scope. So I guess we are exiting here. So that would be in spin lock locker. We're doing an unlock, which means we're just calling unlock on the lock. Sure. Okay. So this is a non-recursive spin lock. We should look at the recursive one. So I guess we need to understand what mlock, what we assign to mlock. So we are assigning it right here. We're assigning 1 to it. Oh, no, this is not the recursive one. Sorry. Recursive spin lock lock. So here we are assigning the current CPU to mlock. Okay. Let's see. So when we lock, we turn off interrupts. We save the current CPU flags, then disable interrupts, then enter a critical section, which just increments the critical counter. Sure. Then we grab the current CPU. Sure. And at this point, interrupts are disabled. So that's should already be good. Okay, and then we're just waiting. What does wait check do? Is SMP enabled? Okay, so we're just kind of pausing or trying to tell the CPU to, chill if we don't get the lock right away. Okay. Once we get the spin lock, then So mlock should contain the CPU that acquired the lock, I would expect. But maybe there's some scenario. I know we have a bunch of irritating scenarios in the kernel where we actually allow you to do really goofy stuff like blocking on a mutex while holding a spin lock and stuff like that. All of that stuff needs to go away. It's just stupid hacks that sort of all come from our big lock mechanism. And let's see. Why would mlock not contain the current CPU when we unlock? Yeah, okay. I'm gonna reboot this machine here, and then I'd like to look at it in GDB. And unfortunately, I killed the VM before attaching GDB, so that was a bit stupid. We can probably get it again though, or we'll get something else. Bum, bum, bum. Okay, so let's run the big test suite. Ah, look at that. And how nice. It's the same one again. Very fortunate. So let's attach GDB. Okay, I mean, it's not the exact same backtrace because it's not in the Chadir syscall, but we are doing a recursive spin lock unlock. And it's happening in core dump. Interesting. So core dump has a spin lock held across this entire scope. And then when we exit the scope, we try to unlock the spin lock, but when we unlock it, we are on a different processor. And that seems very believable because this code is actually totally, this is an example of this totally bogus things you can do. So we're grabbing a spin lock and then we are writing stuff out to disk. And writing stuff out to disk can mean anything. Like it can mean that you have to block on a hard drive or something like that, you know? So you have to go to sleep, you have to block. You should not be holding a spin lock across this operation. The fact that this is possible is, I would say, just a total design bug in our kernel. And I know we've had people try to like panic the kernel automatically if you try to block while holding a spin lock, and it just there were so many things tripping that up. So there's definitely something that we need to improve and turn this into a hard error so that you don't do this. So it seems kind of possible that this is what would be happening. So what was the other situation? That was Chadir, right? So Chadir, now that I think about that, what does Chadir do? So Chadir looks like this, okay. And it has a spin lock protected, which is the current directory is protected by a spin lock. And we grab that spin lock and then we do open directory. Ooh, and this here might do disk IO. So again, a situation where we're doing IO, possibly blocking IO while holding a spin lock. We should not be doing this. So really, this should be done outside of the spin lock. And then we should only like assign to this thing inside of while we're holding the spin lock. So this should look, oh, and we need the current directory for the resolution. All right, so I guess here we have to actually take the lock twice. Can we do something like this? Current directory. And I guess I want a non-null ref putter to custody, right? So something like that. So this is kind of a verbose thing to do, but essentially what we're doing is we are locking this spin lock protected variable or member. When we have the lock, this callback is invoked, and we instantiate a non-null ref putter to the custody while holding it with the lock. So then we should be able to resolve here using the current directory as the base path, and then relock once again. And at that point, assign like this. And this is not going to fail actually, so we don't need to have a try there. We can just do that. Something like that. And maybe, I wonder, like, would it be more elegant to do a swap here? Or maybe you can't do that? Because if you do a swap, then you don't, it's faster to swap two reference counting pointers while holding the lock because it's much less work. You're just swapping out the underlying pointers. Assigning to one means that you have to manipulate the ref counts while holding the lock. So this feels more elegant. I can't do it though because... Oh, one is ref footer, the other is non-null ref footer. So, okay, so maybe I can just do that then. No. Oh, new directory is... Oh, right. New directory is a ref, non-null ref footer. And the current directory is a ref footer. So I need to demote this thing. Note, we use swap here to avoid manipulating the ref counts while holding the lock. Yes. Okay. Or wait. Am I doing premature optimization right now? Maybe I am. But at the same time, I don't feel bad about it. This does not feel like a bad thing to do. We want to, I mean, there are spin locks that we hold for obscene lengths of time, and it isn't right, but that doesn't mean that we have to write new code that holds spin locks longer than necessary. We should try to hold any spin lock you should hold for as short a period as possible. And we need to get much better at that. So let's see. So I think, at least I think that's the fix for Chadir. Let's see if that builds and runs. The core dump issue, that's a bigger issue, I guess. So what's the fix for that? Yeah, this is going to be a bit harder to get right because essentially we want to generate a core dump containing the contents of the memory address space of a process. And while we're doing that, we're taking the spin lock for the address space, which means that nobody else can manipulate the address space while we're doing this. It really seems like we should find another mechanism to ensure that nobody tampers with the address space here. Like one thing is that core dumps actually only happen after the process is dead anyway, so the address space is not going to be manipulated. So maybe we can find another way to ensure this, although I guess perhaps we would want to support getting a core dump for a process while it is running. I don't know. Anyways, I'm just going to ignore this one right now because it's kind of its own little architectural quagmire. Okay, so we're up and running. All right. And let me run tests. I'm bringing up one of these because I like to look at it. Let's start some JavaScript. Where's the crash? Where's the crashing? So I know we're doing we're provoking a bunch of crashes. They happen right here as part of the test suite. So I think that's where we were hitting the core dump logic. But so far so good. Maybe we should try something harder, like let's try to build a Doom in Serenity. So I was just fixing the Doom port earlier today because it wasn't building, so I made it build, but let's make sure we have the latest one. And let's see if we can build it inside Serenity. And then we can see if we can parallelize the build. That would be super awesome. Okay. Okay, so does this work? Just with one make? Seems fine. Okay, so with one make, it appears that we can make Doom. Do we get all the way to the end? Hey, It doesn't quite link due to undefined reference to symbol unwind resume. Wait, what? Interesting. That seems like some kind of a issue with our GCC port maybe, but we were able to get all the way to the end and then linking fails. So let's try that with 2 jobs. Oh, I think we're deadlocked. All right, let's see. Let's get GDB up in here. All right, so what are we doing? Now we're deadlocked, which probably means that the 2 threads are doing something stupid and preventing each other from running. So let's look at CPU numero uno. It's in leave critical, blah, 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 blah. Mutex unlock. Let's see. Thread unblock from mutex. Okay, so we're trying to lock a recursive spin lock. That is what we're doing. In the CPU 1. And then CPU 0 is trying to lock a recursive spin lock. Well, who would have thought? Okay, so let's find out which locks these are. So this one is at scheduler CPP 225. 225. So we are trying to take the global scheduler lock in pick next. So trying to pick the next thread to run, but some other jerk is holding the global scheduler lock. That will be this jerk right here. So he is trying to grab a spin lock here, thread CPP at line 334. Okay, so he is trying to get the block lock for this thread, and looky here, he's already taken the scheduler lock. I bet you that this is going to be some ABBA, ABBA lock thing. We've had a whole bunch of those before where locks are acquired in inconsistent order and then you get a deadlock because you have 2 threads holding the thing that the other one wants. So let's see. So this guy had the scheduler lock. Okay, so we know he has a scheduler lock and he's waiting for the block lock. So let's figure out why this one has the block lock. mutex block, thread block. I bet you that it's in thread block at line 313. Let's see. Block, lock, unlock. Wait, what? Block, lock. Oh God, this is so confusing. I don't love when we do stuff like this, where we have like manual unlocks instead of using the RAII stuff. And here we're mixing it, which makes it even worse. So, okay, so schedule lock, block lock. That seems fine. Schedule lock, block lock. Ooh, but look at this. They are in different order. So this one takes scheduler first and then block, and then releases them in backwards order. That's probably, I don't know if that's hurting us here, but let's fix that anyway. Let's just be consistent about that. Also, let's see. So the expected order is scheduler lock, block lock, right? So let's just see that we are actually doing that everywhere. And block lock. Okay, so here, thread block impl takes block lock before scheduler lock. That would be a problem. So let's make sure that we take scheduler lock first. I think the downside of doing it this way is that you take the lock even though you don't need it in some cases, but we should still be consistent about that. So I think that's still the right fix. Scheduler block lock. Here we are taking block lock, but not scheduler lock. And then unlock. Oh, this code is so in need of love, let's say. But that's why we're here. We're giving it some love. So let's see, scheduler block lock. Scheduler block lock. Yeah, always getting the scheduler lock first. Gotta make sure. Scheduler first. Yup. And we made it around. Okay, so here, at least this is... Wait, we have block impl on the stack here. This is such a deep and confusing stack. 167. Okay, I'm just gonna see if do a quick check here to see if this actually allows us to progress. Oh, we died right away. All right. Now what? Shoot, what's going on? We are in syscall asm entry. Wait, what? I haven't seen this one before. Assertion failed, CPU flags. So we're expecting bit hex 200 to be set in the CPU flags. I guess that's an interrupt flag check probably. So we're entering the syscall handler with interrupts disabled. That's strange. Okay, I'm gonna see if that's a one-off or if I've messed something up. Okay, no, that's not a one-off. Okay. So what did I do to make this happen now? Let's see. Gscheduler lock. We might be missing some other use of the block lock. Is this exposed elsewhere? No. Also, what is lock? Oh, somebody provides us with the lock. I guess that is the mutex internal spin lock. Okay, well, what if we undo this change here? Just leave that one alone for now. And then we leave only the reordering that I did in the block impl to make sure that we take scheduler lock before block lock. Still failing. Okay, I'm suspicious. I'm gonna do I'm gonna remove the disk image and make sure that we rebuild it, because I'm paranoid that sometimes when we're dealing with kernel panics, the system just panics and dies, and then we may corrupt the file system, but it doesn't appear to be related to that. Okay. So what on earth is happening now? Assertion failed. Okay, and let's verify that it's indeed because I've done this. It is because I've done that. That is so strange. So what is even happening differently? We try to set up the blocker, and if that doesn't work, we will unblock immediately without blocking. Which then ends up becoming a system call with interrupts disabled for whatever reason. That is really strange. Let's see. Why might this be happening? Also, are we unlocking these things? Scheduler lock here. Okay. So I feel like I want everything to be unlocked and locked in the same order. I'm just gonna try to make everything look correct. And then we'll have to try to figure out what's going wrong. But this part here looks wrong, right? Because we are taking, yeah, we're taking scheduler lock first. Yeah, so we should unlock it after the block lock. But why would any of this cause a syscall to happen with interrupts disabled? I'm so, Well, now that doesn't happen. What in tarnation? That's strange. Okay, so I am confused. So does that just not happen? Does it happen again if I swap the order here, or is it the other pair? It's not that one. So it's this one then. In block impl. Huh. Well, that is just straight up weird, and I'm not even gonna debug it. I'm just gonna, because this is the correct unlock order. So I think I'm just gonna let it go, fix the lock and unlock order, and then be happy that that it's correct, and then we'll see if we can make progress on the build instead. Make clean J2 and hey, look at that. We are multitasking. It's kind of cool. And we're on multiple CPUs building stuff. That's really awesome. And the link fails at the end. Sure. But that was really sweet. Let's try it again. Oh, we crash. All right. Oh my goodness. Okay. Now what? This looks like a big chunky thing, but it's something else. We haven't seen this before. We are in wait, the wait syscall. In process teardown, it seems like. But how cool is that? We built Doom on two CPUs at the same time. So very, very good progress. Let's go ahead and see. Let's do commits here. So let's do the Chadir one first. Let's see. Kernel, don't do path resolution in syschadir while holding spin lock. Path resolution may do blocking IO, so we absolutely, so we must not do it while holding a spin lock. There are tons of problems like this throughout the kernel. We need to find and fix all of them. Yeah. Okay. So let's see. Then let's fix the lock ordering in the thread blocking code. Wait, my phone is saying something. Oh, JT has uploaded yet another video about writing an emulator in Yacht. I gotta watch that later, but let's continue with this now. Shout outs to JT, by the way, making awesome YouTube content lately. Yeah, so let's see. What was I saying? Fix, use consistent lock acquisition order in thread block. We always grab gscheduler lock before thread and block lock. And it seems we had except in we want to grab, yeah, this appears to have fixed a deadlock that I encountered while building a Doom with make J2. Yes, that's pretty cool. So now, what did we have next? Oh shoot, did I keep closing QEMU instead of keeping it open. But, oh wait, I got the backtrace, so it's all good. Okay, so, wait, is this the right one? Let's see. What are we doing here? We're in the wait ID syscall, sure. And it seems like we're deleting the process. Okay, so wait is calling a process destructor, which tears down the process object, which tries to block on a mutex. Which eventually, wait, so this was a crash, but we lost the crash trace. Oh no, here's the crash trace. Right, thread CPP. Scheduler lock is not locked by the current processor, 309 in thread CPP. So scheduler lock, unlock. So we unlock the scheduler, and then here we verify that it's not locked. And then somehow we come back here with it locked. Okay, that's a bit weird. What is going on here though? Why is the process destructor trying to block on a mutex of all things? That seems like something we don't want to be doing. So let's see. Let's figure out why it's trying to do that in the first place. Where's my GDB? Oh, is this it? No, this is this is the syscall one. Yeah. Okay, I have too many terminals. Okay, here we are. Okay, so mutex locker, mutex whatever. Oh, it's the custody list. Oh, the custody list or the custody cache is protected by a mutex? Well, that doesn't seem right. Also, this comment is totally outdated because it has locking. So let's get rid of that first of all. Kernel remove outdated fix me in custody.h. Yes. Okay. So it's a listed ref counted and it uses a mutex. That doesn't make sense to me. Why would we protect this cache with a mutex? It should not be necessary to block while accessing the custody cache, I would think. Also, why are we running the process destructor synchronously in response to wait ID? That's a bit strange. Process. So historically, we used to, that's what the finalizer task would do. It would sort of do all the grunt work of process destruction in a separate kernel thread called the finalizer task. But now we still have the finalizer task, but I guess the process destructor still, like, it's still gonna run destructors on all the member variables that we have in the process data structure. So one of them is the current directory right here, and also the current executable. So those are both custodies, and because custody is list to ref counted, it means that when you unref a custody, we check if we need to remove it from the sort of the global custody cache. So that would be, that happens in listed ref counted right here. So unref is special in listed ref counted. Listed ref counted is a template. It just, what it does is implements support for an object that is reference counted and also participates in a list. And listed ref counted ensures that we lock the list when deleting something, so that we never end up in a state where something is deleted but still in the list, or something is almost on its way to be deleted but still in the list, and then somebody can sort of take a reference to something from the list right before it's deleted. So it's just to prevent a race condition happening there, basically. But and you can use a spinlock or a mutex for listed ref counted. So I think we're just going to switch. Oops. We're just going to switch custody over to a spinlock because spinlock, because I don't think you don't need to block while somebody else is holding this thing. Whatever they're doing, it's going to be over quickly. Let's see, spinlock protected. Spinlock protected. Let's bump that copyright date, why don't we? Okay. Yeah, okay, so let's look at what we actually do. So when we try to create a custody, we grab the all instances list and then we iterate it. So this is actually pretty inefficient. We iterate all the existing custodies and then look for one that matches exactly the inputs to the create function. If we find one, then we return that. So it's essentially just a cache to avoid creating identical custodies. And we could definitely use hash map here instead, for example, but we don't currently have intrusive hash maps. So our hash maps may allocate and they're a bit awkward. So we try to use intrusive lists for stuff like this. But an intrusive hash map is something that we keep finding things that we want to use intrusive hash maps for. We just haven't implemented them yet. At least I don't think we have. Intrusive hash, no, not yet. We have intrusive red-black trees, but not intrusive hash tables or maps. And yeah, so it's a little bit sad here because we do allocate now while holding a spin lock, but I think that's still okay. There's no blocking IO or anything here, and we only use kernel memory, so you're not going to trip any page faults or anything. Yeah, it's probably okay. It's probably okay to swap it for a spin lock, and then we don't have to deal with the process destructor trying to block in the middle of everything on a mutex. Let's see what kind of listed ref counters we have actually. Okay, so all of them are spin locks. It was only custody that was a mutex. So we're just swapping out the only listed ref counter that was a that was different. Okay, well that feels like, I think that's a good change. And then there are many things we could do better here. I'm wondering, like, if you had, right now, the fact that we have to walk the entire list of all custodies is ugly. It would be much nicer if this were a hash table lookup. So it would be, O of 1 instead of O of n. And I suppose if you had O of 1 lookup, you could also do something like where you do a lookup, and then if you don't find it, you unlock, create the objects, relock, do the lookup again, and then if it's still not there, then you insert the object that you created, or something like that. I don't know what's the best approach to this, but right now I think it's okay to eat the malloc, I guess. This really puts into perspective my micro optimization from Chadir, like worrying about the ref count manipulation in Chadir. Here, when we swap at the same time, doing like a string allocation and a bunch of k-mallocs basically, and this huge list walk and everything. Yeah, this data structure could clearly be smarter. And maybe a hash table isn't the best either. Maybe there's something even better than that we could do. Just haven't thought deeply about it. Let's see. So what if we try to build again? Serenity, Doom. I mean, these are pretty cool. It's pretty cool that this actually works. I think this is definitely the... I haven't seen it do this before. Like, I've never seen a parallel build succeed in this way. Ooh, we got a crash. Panic and internal compiler error. Okay, so there are still bugs, not to worry. What happened? We had a protection violation. Read from this address. Sure, 263.0144. That's here. So where are we? We are in the compiler. So, that's weird. We're in the compiler, the executable, and we can't read from it. Wonder why. Well, that's probably going to be some page fault handling concurrency problem or something like that. Or, and then the core dump fails. So whenever we try to make the core dump, it seems like we may run into this problem here where the one we already looked at, where core dump write grabs a spin lock and does blocking IO, which then leads to rewaking on a different CPU than the one that we took the spin lock on. That's just totally bogus. And we need to rethink how core dumping works so that it doesn't need to take a spin lock like that. That's interesting though. So I guess, what's the state of things that we have right now? So let's do a commit of swapping out custody for a spin lock protected, because I feel like that's fine. Then we don't need to block on a mutex in process destruction. Use protect the custody list, custody cache with a spin lock. protecting it with a mutex meant that anyone unreffing a custody might need to block on said mutex. This, yeah. And all right, I don't know. Let's see if we can provoke some other one. That I don't want to get started on the core dump thing right now, but it would be cool to see some other thing. Oh, maybe we can add more CPUs actually, just to see if we can get some other thing to show up. So we still have 2 CPUs. And so far so good. I wonder what that GCC internal compiler error was. One thing that's definitely happening here is that you have multiple instances of GCC, and then we don't page in all of GCC. We just sort of page in on demand whatever code gets executed. So I could totally imagine that we have some race somewhere where, you know, you have like 2 instances of GCC sort of paging in the same page at the same time, and then something goes wrong or something like that. I wonder what happens if we can, I guess we can just add more jobs. See if that irritates it. Otherwise, I'm going to add another CPU and see how that goes. It's really cool though that it works at all. I say, as it deadlocks. Aha. Okay, now what? Okay, so this CPU 0 is at thread CPP 670, waiting for the scheduler lock. Okay. Seems like it wouldn't really have any other lock at that point, so it's just waiting for the scheduler lock, and then the first one, or the CPU 1, where are we? Process from PID, spin lock protected, blah, blah, blah. Spin lock CPP, wait, no, where am I trying to go? Process 429. All instances. That's a spin lock protected, sure. So we're trying to take the process list lock, and that doesn't work. I'm just going to continue and get a new break in case we get something looking different. Still waiting on the process list, and this guy is still waiting on the scheduler lock. Huh. So I guess this thread right here must be holding the scheduler lock, presumably in the scheduler down here. So then, does that mean that this thing is holding the process list lock? That seems, or was I just not paying attention to that? Update time scheduled. This does not feel related to the process list. Current thread. Who was calling it? Trap frame. Yeah, the backtrace here is not super great. But I don't know why it would be holding the process list log. All right, I think I'm just gonna let this one slide for now, because I've already been recording for quite a bit and we got some good patches. And there's no shortage of concurrency issues, as you can see, but I'm glad that we were able to make progress enough to see some kind of successful parallel compiles. And this will be the end of today's video. So if you made it this far, then I thank you for watching, for hanging out. I hope that you saw something interesting here today. And if you want to investigate and track down concurrency bugs in our kernel, you are more than welcome. We have a lot of them, as you can see, but it feels pretty wholesome to fix them and move towards a place where we could just have multi-core support on by default and then get a lot of testing for it that way. Anyways, that's the end of the video. So thanks for hanging out, and I will see you all next time. Bye.